Hey guys, we're on to the last topic. This is number 3, apply logarithms to growth and decay. And things are as expected are taking a little longer than expected, as expected. So that means we're probably not going to finish early like I was hoping. But I do think we'll finish right about the 75-minute mark. So let's try to speed through this thing. So what are we doing here? We're talking about exponential growth and decay. And for that, we're using this formula, A of t equals PE to the RT. And you might notice this is actually the same thing as the compound interest formula when we had continuous compounding, right? And by the way, guys, don't I'm right. I'm saying what I wrote here earlier, but you don't have to memorize these formulas for exponential growth or for the compound interest. If you need them, I'll supply them during the exam. Okay, in this formula, A of t, or sometimes we just write A. That's the amount after time t. P is the initial amount. Sometimes it's denoted P sub 0, but we're using P. And then the rate, R is the rate. If R is bigger than 0, that's a growth rate. And if R is less than 0, it's a decay rate. T is time in years. It says in years, but it's not always years. So yeah, T is just time. And one more thing, half-life of a substance, sometimes denoted by T sub 1/2 or T sub 0.5. That's the amount of time it takes for the substance to decrease to half the original amount. So like this happens a lot with like radioactive material, or you might have heard of like carbon dating, that kind of thing. Okay, quick tips. When solving questions involving exponential growth or decay, start by writing out the equation. This guy, the guy that I am repeatedly highlighting in orange. Then fill in all the numbers that you know. The one remaining variable is what you have to solve for. And this is what we see in math a lot, right? We have like equation, you plug in the numbers, and then you just figure out whatever is still remaining as a variable. That's the thing you're solving for. Okay, number 2, you might be wondering why we're talking about exponential functions when this section is all about logarithms. And the reason for that is we're going to apply logarithms to solve the things. So let's try the questions. I got them prepared down here. Okay, starting with number 22. If the half-life of a radioactive substance is 10,000 years, what is the rate that is decaying? So let's just make a quick note here. What are the things we're trying to figure out? This is the R. That's the thing we're trying to solve for because that's what it's asking for, right? 10,000 years, that's going to be the T. And it doesn't say right off the bat what your A and P are. You have to kind of surmise it from this statement right here that it's a half-life. So let's write our equations. A equals to PE to the RT, right? If it's a half-life, that means at time 0, when you first start, P sub 0, or just P, the starting position is going to be 1 whole. So I'm going to say 1. And after some time passes, 10,000 years to be exact, right? T is 10,000 years. Then I end up with half of what I started with. So I have this equation, 1/2 is equal to 1 times e to the r times t, and t is 10,000. So looking at this equation, the only thing that's a variable is that r, right? Everything else is a number, so I should be able to solve the thing. Remember, e, even though it looks like the variable, that's a constant. It's not a variable. So what do I do to solve this thing? I got an e. Let's take a natural log both sides. Natural log is the inverse of the e, right? I kind of just ignore that 1 being there because it's a 1 anyway. It's not changing anything. When I apply the natural log of this on both sides, well, left side becomes natural log of 1/2. And the right side, because it's an inverse function of e to the power of whatever, this whole power is just going to come down. This, by the way, is consistent with what we learned about rules of exponents, right? The power comes out as a multiplier, and then I have natural log of e, but natural log of e is just 1. Okay, so anyways, r times 10,000. The exponent came down because I applied this inverse function, right? And now to solve for r, it's divided by 10,000. So r is going to be ln of 1/2 over 10,000. And at this point, I'm just going to plug that into my calculator. So sorry guys, you're going to just not see any movement while I plug this thing into my calculator. ln of 1/2 divided by 10,000. Okay, this is what I get. I get r is approximately negative 6.9, or I'm going to rate it I'm gonna write it the other side so it's easier for me to. I'm just gonna reverse the order. R is approximately negative 6.93147. And then this is how my calculator displays it. It says like this E, and it says -5. And what that means is negative 693,147 times 10 to the -5th. And what that means is that I should move the decimal place 5 times, right? So we're started here. I should move it 5 times to make it smaller that way. What that also means is that I'm going to have 4 zeros. So when you see this negative exponent, if you subtract 1 from that number, that's how many zeros you're going to have after the decimal place. 693,147. Just to double check, look, the 1, 2, 3, 4, 5 puts me right where I'm supposed to be. At 6.9. Oh, sorry, I forgot to write the... I wrote the decimal in the wrong spot earlier, sorry. I read my calculator wrong. That is, of course, it's going to be always right after the first digit, right? Negative 6.93147 times 10 to the -5th. Okay, so this is my rate, and that's the rate that it's decaying at. That answers question number 22. Okay, we're going to see a lot of this happening. What we just did, very kind of similar procedures here. And looks like, actually, looking ahead, looks like all these questions are like half-life questions, which is not always the case, but it is in this selection of questions. Okay, 23, iodine 131, a radioactive substance, is effective in locating brain tumors, has a half-life of only 8 days. Let's get rid of that. So 8 days looks like a T to me, right? Hospital purchased 20 grams of the substance but had to wait 5 days before it could be used. How much of the substance was left after 5 days? Okay, so there's actually 2 steps to this question. First, let's just write our equation. A is equal to PE to the RT. And let's break down that first part of the question up to here. Half-life of only 8 days. So that means after a certain amount of time, 8 days, you end up with half of what you started with. E to the R in how many days? 8. That's the time. So I have the same kind of equation as last time, right? I can solve for R. And the strategy is the same. I take natural log of both sides. And the left is going to give me natural log of 1/2. The right is undoes it. It's going to give me R times 8. Divide by 8 to both sides, I get R is equal to ln of 1/2 over 8. Let me type that in. Okay, so R is approximately negative 0.0866. Okay, it's good practice to keep that whole value that you have as a result in your calculator when you do the next part. Next part says, okay, they had to wait 5 days. How much are they going to have? We're going to start again with the same equation. It's kind of like when it reminds me of, how when we did the variation questions, right? Where you had to solve for K one step and you plug it back in and then solve the next part of the question. Kind of similar. This case says they purchased 20 grams. So 20 grams would be the starting amount. Now we have the rate, negative 0.0866. And how much would be left after 5 days? That's the T, right? I'm trying to figure out what A is. So I just punched those numbers in. 20 times E to the negative 0.0. Oh, actually, I'm going to just recall here my answer. So that's going to give me the most accuracy. Recall my whole answer. Multiplied by 5. Okay, and it gives me A is approximately 12.9684 to the nearest 4. I'm going to round to the nearest single decimal, though. So it's approximately 12. This 9 would round up, so it's going to be about 13.0. 13.0, and this is grams. Okay. So that answers the question. There's going to be about 13 grams. Okay, that's done. Okay, 24. Plutonium-241 has a half-life of 13 years. Laboratory purchased 10 grams of substance, not used for 2 years. How much was left after 2 years? This is like pretty much the same exact question. Different substance, different time, but and it's years this time instead of days, but pretty much the same exact question. Start again. A is equal to PE to the RT. And here A is as a half. We're trying to figure out using half-life, right? So after some time elapsed, we have half of what we started with, half the whole. E to the R, we don't know. And time we do know is 13 years for half-life. Okay, apply ln on both sides. Left side gives us ln of 1/2. Right side gives us R times 13. Divide by 13. R is ln of 1/2 over 13. ln of 0.5 over 13. Okay, so R is about negative 0.0533. And I want to redo this. A is equal to PE to the RT is my starting position. It says they purchased 10 grams. So 10 grams is their P. And they want to know how much is left after 2 years. Rate was, well, we just figured out, negative 0.0533. And this is after 2 years. Yeah. Okay, so I'm just going to punch those things in. 10 times e to the 8.0533 times 2. And answer is about 8.9885. I'm going to round to the nearest single decimal place. This 9 is going to round up. Oh, sorry, this should have been about equal. So that's going to be 9.0. So about 9.0 grams. Okay, so I lost about a gram. Does that make sense? 13 years half-life. So after only 2 years, yeah, should still have most of it. Yeah, makes sense. That's 24. Moving on to 25. Tritium is used in nuclear weapons to increase their power. Decays at, okay, this time they're giving us the rate. Decays at 5.5% per year. Calculate the half-life. Okay, sure. Okay, again, start with our equation. A equals to PE to the RT. And just fill in what we know. We're trying to figure out a half-life. So again, A is half of what you started with, a whole, right? E to the rate is 5.5%, but this is decay we're talking about, right? So this should be negative 5%. So, and what's 5%? 0.05. What's 5.5%? 0.055. And this is t. Now looking at this thing, the only thing that's a variable is that t. So I should be able to solve it. Take ln on both sides. The left gives me ln of 1/2 again. The right side, I got negative 0.055 times t. So t is ln of 1/2 over negative 0.055. We're going to approximate that. Okay, and I got t is about 12.60267. I'm going to round to the nearest single decimal place. So t is about 12.6. And if you wanted to be more accurate, not necessarily accurate, but if you wanted to follow the notation they're using, this is the half-life we just calculated. So that's, you could say it's t sub 1/2 or t sub 0.5. When I say sub, I mean it's a subscript. Yeah. So about 12.6. And what's the unit? Is this years? Yeah, years. Okay, that was 25. Okay. Oh, wait, real quick, guys. 5.5% per year means how many years would you expect it for it to take 50%? Like almost. Uh, oh, actually, no. I'm sorry. It doesn't work out. It doesn't work like that. I was thinking linearly, but this is not a linear decay. It's exponential decay. So it's not decaying in a straight line. Which is why it wouldn't. Which is why it's not just simply like about 10 years. It's actually more. Okay. Anyways, 26, 60 grams of magnesium, 28, decayed into 7.5 grams after 63 hours. What is the half-life? Okay, so again, A equals PE to the RT is my formula, right? And the ending result was 7.5 grams. Starting was 60 grams. What was the rate? Rate is something that we don't know, so it's R. But how long did it take? It took us 63 hours. 63 hours. Okay, so we're trying to figure out the rate first, right? That's the one variable that we got. It's the only variable. So how are we going to do that? Well, we're going to apply natural logs. Oh. Okay. So if I do this now, though, I got this ugly 60 here. And if I try to apply the natural log, well, you could use the rules we just learned and see that's natural log of 60 plus natural log of e to the r times 63, right? And that's totally acceptable. But to me, that's not the most natural, easier way to do it. So natural way to do it is just take a moment, divide by 60 first. Divide both these sides by 60. And 7.5 divided by 60 is 0.125. So I got 0.125 on the left. 60 divided by 60 cancels. So I got e to the r times 63. Now, natural log both sides. On the left, you're going to get natural log of 0.125. On the right, inverse function, right? These guys are gone. You're left with r times 63, and you can just divide by 63. And that's approximately negative 0.03300. Well, actually 0.1. Okay, so that's my rate. Now let's go redo the question with A equal to PE to the RT. Now what is it asking for? It's asking for the half-life, right? So half-life means A is going to be a half, where P is 1. E to, now I know the rate, negative 0.03301. And T is what I'm trying to figure out. So, same usual method. Take natural logs both sides. It's going to give me natural log of a half on the left. And on the right, I'm going to get negative 0.03301 t. Okay, divide both sides by that negative blah blah blah. ln of 1/2 over negative 0.03301. And t is approximately actually it's exactly. Well, I input my full answer instead of this. And it turns out t is exactly 21. And now it's all making sense, actually. Watch this. T is equal to 21. This is hours, yeah? T is 21 hours. Watch why this makes sense, guys. So T, this is the half-life, right? T sub half. Okay. Look, we started with 60 grams. We ended it with 7.5 grams, right? 63 hours is the total time that elapsed. It so happens 63 divided by 21 is exactly 3. So that's three half-lives that transpired, right, in 63 hours. So that means from my starting position of 60, I should divide by 2 3 times. 60 divided by 2 divided by 2 divided by 2 is exactly 7.5. So it all matches up, right? After 3 half-life periods, my initial value was divided by 2 3 times. The end result is 7.5. So that means we are correct after all that work. Could have actually probably figured out a different way, but this is the natural way to do it using the formula. Okay, guys, we're done. I'll see you next time.